Alright students, so we're about to solve a problem dealing with momentum and collisions in two dimensions where we're going to have, rather than just one item collide with another all along the same line, we're going to have these things moving in vectors, something kind of similar to what you would have in on a billiards table or a pool table when a pool ball has both maybe an X and a Y motion. So what turns out is that when the motion of the collisions occur in two dimensions, you can actually break down the momentum into its x components and its y components, and then momentum is conserved in the x direction and momentum is conserved in the y direction. So this is a little bit backwards of what we normally write in class, but we can get the idea. The momentum of each object in the x direction, you add it all up, and that's equal to the momentum in the x direction of each object, if you add that all up, after the collision. And the same thing for the y. So let's go ahead and look at a problem. Alright, so here's our problem. We have two pucks of equal mass. They're both 100 kilograms. They collide on an air hockey table. We're going to neglect friction. And prior to this collision, prior to the collision, we've got one puck traveling in a direction that can be considered in the positive x-axis at 1 meters per second, and puck 2 travels in the negative y direction at 2 meters per second. And then after the collision, we've got puck 2 traveling at 30 degrees above the positive x direction, that is above the x-axis, at 8 meters per second. What is the velocity, the direction and speed of puck 1 after the collision? You're like, what in the world? Okay, this is a nice big block of text. Well, let's go ahead and draw a picture here. So we've got puck 1, positive x-axis, going at 1 meters per second. Puck 2 traveling in the negative y direction at 2 meters per second, so moving downwards. After the collision, puck 2 travels 30 degrees in the positive x direction, so 30 degrees above the x-axis at 8 meters per second. And we want to figure out what is the velocity of puck 1. We're going to assume, since they're colliding, it's probably going to be going down here. If we're not totally sure, we can just draw it here, but the angle that we end up calculating in the x and y coordinates of the momentum, the x and y components rather of the momentum, will tell us exactly which quadrant, whether even if it bounces back completely or goes down here into the third quadrant. But we'll assume that it's going to go into the fourth quadrant, something kind of like that. So, like we said a moment ago, we can actually break down the momentum into the x and y parts. So we could say what we're going to do here is just sort of make a little table of the velocities of the objects before and after. So the velocity of object 1 in the x direction initially is 1 meters per second. The velocity of object 1 in the y direction initially is 0, so it's just moving left and right. The velocity of object 2 in the x direction initially was 0, and in the y direction it was negative 2 because we saw it was moving downwards. After the collision, the velocity of object 1 final in the x direction, we don't know. That's one of the things we're looking for. And in the y direction final, we don't know. For object 2, we're going to have to just do a little bit of trigonometry right here. We know that it was traveling at 8 meters per second, or rather 0.8 meters per second at a 30-degree angle. So we can use our trig 0.8 sine 30 and 0.8 cosine 30 to break that down. And the x value turns out to be 0.4 meters per second. That's this direction right here. And the y direction is 0.7 meters per second. That's just to show you what's going on right here with these values right here. Sorry about that. About the actual x direction was 0.7 and the y was 0.4. Sorry, I think I had that switched there on that slide. All right, we'll make sure we get it right here in the equation. So conservation momentum for each axis separately. So just looking at the x-axis, we can say mass 1 v1 x in the x direction initially plus m2 v2. This is of course all in the x direction equals m1 v1 final, m2 v2 final. Since the second object, that second puck, was not moving left or right, it was only going straight down, we know that this is actually 0. You can also look at that table that we just made. If we plug in the values, we have 0.1 for the mass of object 1, it was traveling velocity of 1, plus, just if you want to make it a little bit more explicit, 0.1 times 0 equals 0.1 times velocity of object 1 in the x direction final. That's the part that we don't know. We don't know what it's doing. Plus 1 times 0.7. So that is the correct number right there for the x. If you set this equal to 0, subtract this from both sides, and divide by 0.1, we end up with a nice velocity of object 1 in the x direction final of 0.3 meters per second. So it is traveling to the right. We can do the same thing in the y direction. So basically m1 v1 plus m2 v2 equals m1 v1 m2 v2. Notice all in the y direction. As we start to plug these things in, we notice, for instance, the velocity of object 1 in the y direction is 0. Plugging in our mass and our velocity of object 2 initially, and then after the collision, m1 v1 final, we don't know what puck 1's final velocity is in the y direction, but as we said earlier, we do know what puck 2 is. If you solve this, basically this goes to 0, this term over here, subtract this product from both sides and divide by 0.1, we end up with a nice answer of negative 2.4 meters per second. So that tells us that the puck is moving downwards at 2.4 meters per second. What we can do is we can actually combine those two pieces of information. We found out that puck 1 had a final velocity in the x direction of 0.3, in the y direction of negative 2.4. So we can just use good old Pythagorean theorem there, 0.3 squared plus 2.4 squared, sum that up, take the square root, and we end up with this final velocity vector of 2.42 meters per second. And once again, using a little bit of trig, inverse tangent of the y over the x, and we get 83 degrees below the positive x-axis. And so it turns out that is actually in the fourth quadrant, just like we were thinking. And we're happy that this problem is finished.